Good morning. Now we have the second part of our tutorial about estimations reliability in coherent system. Yesterday, the main idea from yesterday was how we can try to solve problems bring it into simple structures. So the main idea of yesterday was how I can change my problem, how I can rewrite my problem to make it simpler to be solved. This is the main idea. Of course, we had a solution for in the cases of independence of components in other situations, but okay, this is our main idea for yesterday. A few more details now. I should say a few things that I forgot. If you look at this, we were in a series parallel system, a simulate data about this. And we can solve for each component. We only have this kind of structures, a solution for this, and we can build or translate for our structures. But two things are important here. This is on a simulated data, so it's important to know how this data was simulated, how we'll produce this. Of course, we know that we only have the information of time t and who is the responsible for the failure. But how I do that? For a simulation, we don't have too much different from we generate one sample of y1, y2, y3, y4. Then we evaluated this maximum, then the minimum of both maximums. And at the end, we register t and delta, because we know all the values. However, to simulate, we needed to know all the values, but the only information that we keep registered for the estimators are just t and delta. This is the way that we can simulate this kind of system. Okay, so here also, for our simulation, we are considering that the components are independent. Another important detail is, if you take a look here, in some way, in some part, this estimator is bigger than the true distribution. If you look here, the same is happening. So I told you yesterday, oh, this is quite good. Yes, it is quite good, because we have, where is? We have a lot of sensor. So it's quite hard to work under this scenario. But there is a reason for this too, because if I am working in a series system, what I am saying about the sensor time is bigger than some value. So the information that I am given when I have sensor is bigger. So probably this will affect our estimations in some way, that I will give more chance, or my distribution will be bigger than the true, because I am saying, oh, the system failed at time 5, and the other one failed after 5, but after 5 can be 6, 7, 8, 9, it can be anything, and probably this component will be failed at 6, but I am giving the chance in the model to this component failure at 20, 23, so we have this kind of problem. It's not exactly a problem, it's the nature of the estimator. At the same time, if you think in a parallel system, what we are saying is that it was before, so I am decreasing the estimator. So we may have here not exactly two problems, but two conditions that are important to say. We may be underestimating our reliability function, or we may superestimate be more than should be. However, we did some studies about this to be sure of what is happening, And generally, this kind of problem starts to happen when we are some way far away from our data. So probably for this component 3, after some point here, we have only sensor times. So it's something like to say, how I can have this kind of estimator without have information in this part for this specific component. I only have sensor in some way. So this is a problem, but also is the best solution that we can have it. Moreover here, I forgot to tell you yesterday, but if you think in a frequentist way, all that we did here can be used for frequentist estimation too. Why you did not that? Because Bayesian is more nice, just that, but it's possible. And here, the most famous solution in statistics for a series system is known as the Kaplan-Meier estimator. So if we come back, I will not come back now because it's many slides, but if we come back to the beginning of solutions for a series system in a non-parametric perspective, the exactly counterpart in a frequentist way is the Kaplan-Meier solution. And what is the I found a few, 1-2 years ago, a version of Kaplan-Meier for parallel systems, but I never read about frequentist non-parametric solutions for these more complex structures. Okay. Yes? Sure, sure. Yeah. 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 This is, thank you for the question, because there is an important detail here that we are talking about 100 observations of the system. So I should say 100 in this kind of conditions, it's a small sample. But if you think, I will do an extreme example. If you think that I am analyzing the reliability of a plane, I should crash 100 planes. So now this is quite crazy. I cannot do that. This is an important matter because the sample size is important. We need a huge sample size, but I don't have it. I have to work, and generally in the when you are working here, probably you will have 10, 15. When we have a sample of size 30, we are happy because it's so yes, we have this problem, and the most important here it was in simulations. But I will not say exactly because I don't remember right now. The bias here or the error here, in general, in 100 samples like this, because this picture is not so good to see exactly, but in general, this bias or this error is around 2 to 3% or 0.03 in errors. And if you are thinking that this mainly occurs in the end of the distribution, we know that in this part, this kind of error is not so important. Generally, we are more worried about the beginning here. If you think in a manufacturing company and the warranty, I should have a great or a really good estimator in the beginning of this to guarantee to have sure about the working here. So It is a problem, yes. We need a huge sample size. I cannot say precisely how much. But this is not exactly a huge problem, at least not in this scenario. Of course, if I change for another scenarios, this may be complicated. At the same time, it's quite hard to find a better solution here. So it's something like, I am here and I want to pay the price for have this kind of solution, or I prefer to not look to that. Something like, okay, this is not a great justify, but it's something like that. However, this is the good part. We should move on. So we may solve this with a parametric structure. Yeah. But this is important because we should explain all the details. So, yes. Here, recalling from yesterday, I told you, we have these structures and the same component can be in two parts. It's a logical structure, it's a diagram and a way to represent the system. So, if we think in a bridge system, we can have this kind of representation in this kind of representation. And here in the non-parametric way, I am telling you, we can solve this problem. But now, we have, for example, component 3 in two parts here, or two parts here. And we need the independence of the components. And for sure, if we use this structure, it's not only dependent, it's the same component. So I will not be able to solve for all components here. In this case, I will not be able to solve any of the components because 1 is here and here, 2 is here and here, 3, 4, 4, and 5. All components are more than once. I will only be able to solve if the components appear only once. So, okay, this is, and when we were working here, our idea was, I want to solve this structure and have an estimator for a bridge system. And when we finish this part, I do not have it. I only have it for problems with independence. Okay. Unfortunately, we cannot solve it here. But now we go for parametric models. We can look at for the Bayesian parametric models. What is an advantage or may an disadvantage of a parametric model? In some way, when I am using a parametric model, I am giving a structure for the problem. I am giving more information to my model because I am limiting what can happen. In the case of non-parametric, working under a multinomial model with Dirichlet multivariate process, we are not giving restrictions for the distribution functions. They can be anything. However, here, under a parametric model, for example, if I choose a distribution like exponential distribution for my components, I will only have exponential reliability functions because I am giving this structure. So I am putting information here. Okay, so doing in this way, now we have again our aim for, at least for now. I want to solve this problem. How I can work here? How I can do that? So we have, we will change a little our way to look at the problem. No, we will change a little the notation because we will need some different way to write this. And if you think now more like a survival analysis, what we are doing, I have a component that I can see the failure time, or I will be left sensor or right sensor. But we have one more structure in survival analysis that is the interval sensor. And when we were working in this kind of problem, it came to us, why I cannot use this to solve the reliability problem and this idea. So we can have these three kind of sensor types. Oh, sorry, here is just two and unsensor, but we can look into this like an interval problem. For example, the component, I put the system to work and the component is working until some time, and I know that it's not working after some time. I know that the failure of this component is in some way between 10 and 20 hours. This is a kind of interval sensor. I know a lower bound and an upper bound for the failure of this component. We have it. We don't have it exactly in this way for reliability, but this idea, what we can do here, we can call a right sensor problem as an interval. What is the interval for the right sensor? 20 until infinite. What is the interval for left sensor? 0 until 10. And the specific failure time. Why this solution is interesting? Why we are trying to look and why we want to use an interval sensor to represent our problem? So, using this idea, we can have this notation that is, if we write now as an interval, the failure time of the component and the lower value and the upper value are equal, then I have the information and that component failure at that time. If we have the lower value equal t and the upper value equal infinite, this is right sensor. If it's 0 and t, left sensor. And if it is two different values, they are interval censored. Okay. So this is now how we can express this kind of data. Here we have an example of 10 values for the bridge system. What we are doing now is, in some way for a non-parametrical approach, we needed to look into the whole system and we needed all structures of that system and we needed the information about everything we have there and independence of the component. Here, when we write the data in this way, if you see this, for example, the system 1, component 4 was the responsible for the failure of the system. Component 3 is left sensor. Here is right sensor. But look at this data and forgot component 2, 3, 4, and 5. Look only to component 1. What information I will need to solve my problem now for component 1. So what we are doing is, if I look only to the marginal distribution of the component, the information that I need of the all other components is how to represent this data. It was right censored, it was observed, it was right censored. So looking only for the component data, we will be able to build a model for this component. And now I will not need the independence structure when I have this built. Okay, so the main question here is, if I have 1,000 of components, the only thing that I need to solve here, for example, if I am interested in only one of them, is a kind of data represented like this. I use all the information to build this representation data. But when we do that, we will be able to handle and write our model. What is our model? For that component, for component J, we will have in our likelihood the density function when is not censored. And when we have sensor, it's right. We will have a difference of reliability functions. What is the difference of reliability functions? What is happening here? We can write this just like the probability of this component failure between the time L and U. So the importance in the likelihood of a censored observation is the probability of this component will failure inside this interval. If this interval is between 0 to something, then we will have here in the lower bound 0, and this will be 1 minus distribution function. So don't be worried about the signs. This is always positive number, and it is a probability. If we have the other part, sometime until infinite, this will be infinite, and this will be 0. And, okay, if here is 0, this 1. If here is infinite, this is 0. If it is an interval, it's the probability of being inside the interval. This is the contribution to the likelihood. Okay, so what is our model here? We have a likelihood function for each component. So now we are only looking to the component. We are not looking more to the whole system. I only need information for this component, and I don't need the restrictions of independence between components now. It's something like I change the way that I am looking to my problem for a way that I can solve it in a simple way. And what kind of model I can use here? Anyone? If you want to use a exponential distribution, yes, you can. If you want to use a log normal distribution, yes, you can. A gamma distribution or any distribution that has the domain in the positive values. Why positive values? Well, I don't think that's possible to have a component that will fail before 0. The component will fail with time minus 1. This may sound strange, but it's not so unbelievable that we can have this time minus 1, and I will explain why. So we choose one model to work here. And what model that we choose? Well, Weibull model. We work with a Weibull model. Why Weibull model? Well, in this case, I should say, because I like it, and because I am using Weibull model for a long time, and I am always having great solutions with this model. Of course, we could use a more sophisticated, a more flexible model, a more... okay, so we are not using the most used Weibull model. We are using a Weibull model of 3 parameters. Why 3 parameters? We have these location parameters, scale parameters, and shape parameter. This location parameter here, it's important, and this is a great point here in this model, because I told you, how can I have a time of minus 1? And I will say to you that, how you can be sure that the system that you bought, it's new? Maybe someone used this component for some time, and we don't know exactly, we don't have the sure that this is really new. So when we are calling here a negative value for the time, maybe what I am saying is, they sell this for you as a new component, but probably he was used before. Also, this is an important detail. With this kind of parameterizations of Weibull model, we can show, we can prove that we have approximations for normal distributions, logistic distributions, gamma distributions, log normal distributions. So the Weibull model has a simple structure. We can write the reliability in a really simple way. We can write the density functions in a really simple form. This will be good when we will working in the likelihood function, because we have a closed form for reliability function. We don't need here, for example, if you are using a gamma model, we have that constant, the gamma function, Then we are working with a gamma model. This is quite complicated to solve in a computer because this function, oh, okay, I know the solution for some, but I need approximation for that function. So also working in the Weibull model, our computations will be easy because, well, we will need a lot of computations for the estimation process. I'll go in there sooner, but the main idea here is this. In this way, this model can be used in the almost, he's closer to almost distributions, unimodal distributions, of course. If I don't have a unimodal, maybe this will not be right. In the survival analysis terms, that is very easy to look at the risk function. This model can have an increase hazard rate, can have a decrease hazard rate, can have a constant hazard rate, and it's quite flexible in terms of hazard rate here. So this is why we are choosing this structure and this model. But of course, if you like another model, you can just change it for what you want. Okay, so I just talked about this. Why using the 3 parameters Weibull model. And here we have now a little discussion about prior inside this model. There is another, in some way, another advantage for the Weibull model that we can show if we take a prior like this, and this is an improper prior, this is not integrated N1, in some way, it is a non-informative prior, but on a prior with this kind of structure, we can show, well, the posterior here is just proportional, but we can show that using a prior like this, the posterior is proper posterior. So using a non-informative prior, for me here is just a constant, we are able to produce inference, and the posterior is a posterior distribution. Yes?
I can't help interrupting here, I'm afraid. It is true that you will often get proper posterior from improper priors. The cost of that is your evidence time is 0, so that objectively you are infinitely outclassed by anyone who does something wrong. This does not invalidate your results, but you are cutting away half of basic analysis.
I am not saying that I agree with that, because I don't like this kind of priors. I prefer subjective priors. This is important, but sometimes what we are saying here, even under this scenario, it's possible, and we have a posterior distribution, but okay, so I really want to do that? Probably not. And this is another important fact that we are using this model. At least us that are working in this, we have a quite good experience to use informative priors here. We know a little about this. I will share with you guys a few details about this Weibull model. I am working with Weibull model in survival analysis for some time, and many of my friends came and discussing a survival problem with new distributions because the Weibull model is not working. But after work a lot with this Weibull model, I learned one thing. When you are using a Weibull model, try one just simple thing. Put your time in a scale between 0 and 5. How I can do that? Divide the time by 10 or sometimes by 50. You can shrink your data. It's just a transformation of the data. No, it's quite simple. You are just multiplying by a constant. When you do the final analysis, you can just do the inverse. Why this? The Weibull model has a much better behavior in this space. If you have your data between 0 and 300, sometimes your model will not so good. But if you shrink, just dividing by 6, 7, then you probably will have a great solution. How I know that? Well, because I already used this model in many situations and in many practical problems, and then doing that, almost sure this is one of kind of transformations that I used, but the Weibull model is starting to work much better because this is my point of view too. If you are using a parametric model, it's important to understand how your model working. It's not like, no, I am doing something to put inside my model. No, no. I need to know how my model works and how I should use my model. Sometimes, sometimes we need a different distribution, a different model, but maybe it's just the way that you are looking to the data. Transforming the problem make your life easy. Yes, we have this prior. I have this discussion that the proper is prior, but I prefer subjective ones. At least for me, it's quite clear about that. Here in this example, we are working with this kind of prior because we are saying we are not giving our information to this model, and let's see what the result is around it. I know that this claim is not so true, but sometimes it's good to use in this way. Okay. So here the estimation process. We have a posterior like this. Of course, we can change the prior here for anyone that we want, but doesn't matter which one we use here. We will not have a closed solution, analytical solution for the posterior, at least not inside this model. So we will need to do some Monte Carlo Markov chain methods or Markov chain Monte Carlo methods to solve this. The good part is, at least in the way we're working, we don't need a huge sample to discard. So this Monte Carlo is in some way easy to build. And here we are just using a quite simple Metropolis Hastings algorithm and a multivariate Metropolis Hastings algorithm because we have 3 parameters, and then we just use it, in my point of view, a quite simple algorithm. I will not go further inside this Markov chain Monte Carlo methods because, well, our focus here is reliability, and I am sure that Ali will talk more about this kind of approximations, and I am sure that you'll be more interested to listen here than I spend more time inside this Markov chain. So I would like to do an advertisement now, and all of you I am inviting for tomorrow to tutorial of Ali. Thank you. Getting back to the talk, we just need a simple burn-in sample, the jump between the samples. What we use a jump between samples? We are trying to not have autocorrelations between samples. It's not that they are exactly independent, but they don't have autocorrelations, and we need a small jump of samples. And our sample size at the end will be 1,000 of samples. So we will need here to generate in 20,000 of samples of this posterior using the Metropolis Hastings to have a sample of 1,000. And this is quite fast to be run. For verify convergences of these methods, we used some graphical techniques, ergodic means, the quality of the chain, and a few more things. Of course, we can do easily Gilwick methods or Gelman and Rubin. And well, here it was quite good that we just don't give it too much problems to this Markov chain Monte Carlo method. So, okay, once we have our sample from the posterior, we will have a sample for this three-dimensional posterior. So we can now work in using this, and an expectation, a posterior expectation for our reliability function of component G can be approximated now given a sample of theta values. We are calling theta here by the triple beta, eta, and mu. So we can just use this and do an averaging about every reliability here. One important thing that I call attention is sometimes it is common to see we generate in a sample, take the mean of betas, the mean of etas, and the mean of mu, and plug in here. I don't think this is quite fair, because you are doing something like trying to find a maximum likelihood estimator and put in your function. The maximum likelihood estimation has an invariant property. Here we don't have it. And it's quite simple to do that. It's less than 1 second to compute this. So for each sample, we have one different reliability function, and then we take an average of these functions. For average, this is not a problem, and we have a good approximation for the expectation. Okay, so let's now go to another toy example, but now we have a difference. In our first example in non-parametric solution, we had there gamma distributions with different means and different variances, but all of them was gamma distributions. Now we change a little to a Weibull distribution, log normal, gamma, and gamma. Of course, some of you can say that, this is not really different distributions, because all these three models in some way are very similar. But they are similar and not are the same. So we just did this. And the means here, it's quite different. We have since from 15 to 20 and different values for standard deviation. To generate our bridge system, we do similar of what we did before. We generate all values, then compute t. And for each component, we see if it was not censored, left censored, or right censored. So we work on this basis. And the data for a 100 bridge system was generated. And here we have the percentages of censored values. The component 1 has 31% of left censor, 52% of right censor, and a total of 83% of censored data. So I only observe for component 1, 17% of failures. All others are censored and not only one type of sensor. Generally, when we have just 30% of sensor and one type of sensor, this is incredibly huge. We are working here with a lot of sensor. This component 3, that component that is in the middle of the bridge system, it's quite hard to find a system that the component 3 was the last one. In 100 simulated data, this happened only 11 times. So this is quite a challenging scenario. And let's see some pictures. For component 1, the red line is the Weibull distribution function with mean 17 and standard deviation 2.8. So we have this red line, and the dashed dot line is our posterior mean. And now we can discuss a little better, because we were worried at some point in the non-parametric estimator if we could have a good estimator for the points. And I should say one thing there that we don't have it. We don't have this region, this band of credible set. So we are not able to do this yet for non-parametric estimator. But here in the parametric one, it's quite easy to do that point by point. And we have a good, some I will say, error measure, not the error measure, but I can say that my function is in some way, this is what I am expecting, but I know that this is not exactly where we have only mass, because we have a full posterior, we have a full distribution, so we can use it. And even here, in the end of the line, we are quite far away from, the mean posterior is quite far away from the true, but the interval is quite good. So I can know more about what I am doing. I can know that I may be wrong. Well, in some way, we have a way to say, if you are doing statistics and if you are using a model, you are 100% sure that you are wrong, because this is the model. So it's never the true. And okay, so I am sure that this is wrong, but I have a good way to see how much it is. If it is interval, it's smaller, it shrink closer to the posterior mean, this means that I have a great point. If it's more larger one, then probably I will need more samples to improve my estimator. So we have in some way how to see that and how to improve what we are doing here. This is for component 1. Yeah, for component 2, if I only show this picture, then I can go out now because it was almost perfect. And in this case, it's quite intriguing because we never expected something like that. When we look at these pictures, then we'll see maybe we have something wrong, because how can be so close to that line? But well, this is what's happening, and I have 71% of sensor time. For component 3, that almost 90% of the observations are censored, we still have a great estimator. Component 4, here at the end is a little worse, okay? But it's also inside this credible interval, so it's not so bad too. This one is the one that I can say, yeah, I'm not so happy with this estimator. So why I'm saying that? Why I'm not so happy with this one? Because here the interval is starting to be huge. At the beginning it is smaller, but the end, I am looking to this and I'm not doing a good estimator for component 5. And what is important here? We are looking at component basis. So please do not compare these pictures. These are alone pictures. We have a model for component 1, we have another model for component 2, we have another model for component 3, 4, and 5. And now, I should call the attention for an important fact. So I have the estimators of all components. How my system is working, what I can do about my system, I cannot. I am not looking for the system reliability. I am looking for component reliability. So if I wanted to understand the system, well, I can do it. But how I will do it? If I consider in this way, there is no sensor time for the system. I have sensor time for components inside the system, but for the whole system, I am always observing the failure time of the system. So the same model that I am using for all these components, or let me say here, for the system, I have this same likelihood function, except that this part will not be here, because all times are observed. Then I can just use a model directly for the system. So this is one point that we are talking here. We are looking to marginal distributions of components. If you are interested in the system reliability, you look to the system data. Okay. So we don't have it. Here, not, because it was not what we were trying to do. However, we lose a little here. So one disadvantage is, I say it yesterday, when you put all components together in a system to work, we have a problem that it is, I know that they are not independent. Here I don't have the restriction of independence, but also I don't have any information of the dependence. So in reliability should be interesting also to say, sometimes I have two good components, really good components. When I put these two together, it's not necessarily the best system because they may have some behavior in kind of relations of the functions. Sometimes it's made that the system will be better if we have not exactly the best components. But when I put them together, they may build a better system. So yes, we are not estimating these relations, these correlations, and no, we are looking to component basis, we are looking to systems without sensor. Another thing that I can say here, when we think about system, I said also yesterday, look that as a logical way, in a logical form to represent the system. The current or the parallel series systems is on a way to represent these systems. But here, what I am calling in your attention is, I had one example. This example is from the 70s. And a computer program working for magazine stores. They should handle with all transactions of these magazine stores. What we do now at the market, which is quite simple, you take your product, put in your machine, and the price is there. It was quite simple to do this today, nowadays. But in the 70s, we need a real room with computers, a lot of energy, and the system was producing failures every day at 7 p.m. And nobody could understand. The problem is with the software. The software is producing these failures. What is happening here? And after 1 week, looking to the computer, looking to the software, looking to all problems inside, it's everything good, it's everything right. And okay, so now let's look what happens at 7 o'clock. And then working in the computer room, one guy listened a huge sound. What is this sound? Oh, the guys are taking the stores, using the elevator and putting it back in the shop for the customers. What? Yeah, they are taking our stores with the elevator. And then they were using more, putting more weight in the elevator that should be. This was needing a huge power to work elevator. And this power was affecting the computer. And the data was completely corrupted. Everything stopped to work. And nothing is right there. So when we are talking about a system here, don't think that the system can be only the machine that you are looking. Sometimes the component of your system can be the electric power, can be another example. This I think it's in the Meeker and Escobar book, I'm not remember now, but they put one machine to work together to the REIT system of the shop. So when they turn on the REIT system, yeah, the shop was more warm in the winter, but the machine was failing. So it was not exactly a problem of the machine. So here the system is not necessary only what I am looking, only my machine. May I have other effects? And in a logical way, I can do this representation. I can say now that the elevator is a component of my system and is producing failure of my system. So anything I need, I can add in this representation, or I can get out in this kind of representation. So this is the bridge idea, and we can look at to a simple one, a parallel system. Yes, we can also solve the parallel system models here in the parametric approach. We have, we call this simple because parallel our mind, it's easy to handle because all data will be left censored or observed. A system with 3 components, we generated the data, we have this kind of representation, and again, a lot of sensor time. And now if you see this picture, may you say to me, but for the bridge system was better. It was more complex structure. It should be more complex to solve it. Remember that we are looking to component basis, so it's not exactly so important how is the structure of the system now, because we are looking to that component. When we translate our information for only components, we are looking for the component 1, component 2. So the problem is exactly the same. If you are looking to a huge problem or a simple problem, our representation will be always the same. You are looking in a marginal distribution of this component. However, I can say here, so why these are looking worse than before? And it's quite simple, the answer. We have only 30 components, only 30 observed points. And here we had 100. So, of course, less than 1/30 of we have before. And here, what is important? If you look to this picture, you can say, but this is quite bad. Remember, if I have 70% of sensor in 30 samples, we are observing 30%. Less than 9 systems was observed with failure time. So our sample is really small. We only have 9 observations, 9 full observations of this component. So, yeah, I can say at least this is not a proof, but my point of view, this is quite good. This is really good, mainly because we also have these credible intervals, this credible set for the posterior mean. And our model is a 3-parameter model. So one more important thing here that I can tell you is, why is happening this? This call our attention because it's coming in one and then some point just start to get down. This is the effect of that location parameter. What that location parameter is doing here, at least for some samples, is that he is a positive value. So he is putting our Weibull function a little bigger than was before. So this is the effect of this 30 parameter, and then we can work on this. Okay, so now we are moving forward to another kind of problem. We did the non-parametric apportions with independence problem. Then we move forward for our parametric solutions. Now we don't need independence, and we were able to solve the bridge system. Oh, nice. But we are also needing the information about who was the responsible to the failure. And this is not always true. It's quite hard to find or to have this kind of data. Moreover, to have data and knowing who was the responsible of the failure and who components was working and what one's components was not working. This kind of information is not simple to have it. But now we can go forward to this problem of masked data. What is a masked data? We have time of failure, sensor time, component structure, and now we are adding to all these structures a masked data problem. The idea of masked data is, in the beginning, I observe the failure time, but I don't know which component produced that failure. But I know a set of components that produce that failure. What this mean? If I have a system with 10 components, don't take attention to the structure. I have 10 components. In 10 components, the system failure at time 5. And I know which components produce, no, I don't know the component that produced the failure. But I know that the set of components 1, 2, 3, and 4 was responsible for this failure. So it was one of these. I don't know which one. But I know that was this small set of 4 components. So I don't need more all information to solve the problem. What information I need is, what was the possible set that produced this? And now we are going back to the structure, and the structure is important because in some cases, I even don't need to know too much about my system, but if I know the structure and the failure time, I know how I can build this kind of sets, because in some structures, this is given to you by the structure. If this component failure or this part of the system failure, I already know that was just 1 or 2 that produced that failure. Or independent of the structures, you may have this kind of idea. So what we are trying to work in here is in a more general problem with less information, not only sensor information, but also a masked information. Here 2 examples of this kind of problem. When we have some large computer systems doing a lot of analysis you are doing a lot of time, probably Google are doing this right now. We have, I don't know where was the problem, because there is a lot of things working together, but I know that probably, let me say in some way, we have 10 computers working, and inside this computer I have a lot of programs, a lot of things working. I know that I have one failure, but was in computer 1. Computer 1 has a lot of components inside there. So I know that it was one of them, but I don't know which one was. Or another problem, we will not work exactly with this, but this is another example, that is the requirement problem. If you have a system working, sometimes you don't know which component was broken, and you change all of them. A more simple example of this is, if you think in your television nowadays, when your television has a failure, it stopped working, sometimes you go to the guy to fix it, and he look at, I know that is the main board that failed, but probably some component inside there. Okay, so you fix the component. No, it's simple to change the full board because it's less expensive. So you just take off the full board and put another board there. For the guy that are fixing the television, okay, my television is working again. But for the component that do or produce this television, I need to know the reliability of these components. I just know that was the board, but why I need to know the components? Because I want to improve the quality of my television. So I want to know the distribution of these components. So here we are producing a masked problem. Again, we will use the 3 parameters Weibull model. And now this is starting to be more interesting because with masked data, it's more often common to have used components. We don't have exactly the component of that produced the failure, and then we call this by a set, and we use the index S to represent this kind of problem. So now a quite complex structure. In some way, this is not parallel, this is not series, this is not bridge. This is an 2 out of 3 representation of a system. What is the 2 out of 3? A simple way to explain this kind of problem is, if you have a plane with 3 turbines, 3 engines, I am saying that I needed 2 of these 3 engines working. Then I am safety. So if you have a plane with 3 engines, if one failure, you are quite good. You can cross the ocean, no problem. If you have 2 broken, then you may have a huge problem. So one idea of this kind of problem is, in some way, is a redundance problem. You don't need to have exactly all of components, all of them in pairs. But you can have sometimes, you just add one, and you will really increase the reliability of this. But this kind of data is quite complicated because the representation of these 2 out of 3, it will be always 2 components here, 2 here, and 2 here. And if you have 2 out of 10 or 3 out of 10, and this is a quite complex structure. And this kind of structure, there is a lot of them in everything that we use. This kind of problems is inside the television, cell phones, computers. Sometimes when the manufacturers want to improve their system, instead they change and use a better component what they are used to do, build this. So there is a huge chance now that all of you that are with the computers here, probably some components already failed. But you don't know because your computer are working. You may are using a structure like this one. So, okay, in this case, we may have an option of a masked data that I know. Component 1 or component 2 produce the failure. If I have a unitary set, then I know each one was the component that produced the failure. But now we will need another notation. So we have failure time, sensor, masked. Every time that we are adding something, we have also to add some notation. And here I should say something like, we are sorry about the notation here because this is quite complicated to build, and even us are not happy yet with the notations that we are using. We think that we should improve, but it's working. It's possible that it's starting to be a little more confusing because this notation, it is confusing. And why it is? Now we are adding a k value. Yesterday we had a delta value that is working, not working. Now we have for the component, so now is not the component that's working or not working. Now is this component was one sensor, is left sensor, is right sensor. After that, I also need, it was the responsible of the failure or not. It is inside this masked structure or not. Also, we will keep this delta indicator, but now the delta indicator is, he is inside the set of masked data or he is not in this set. So it is possible that it was the responsible for the failure or it is just a sensor component. For working in this way, we will need this conditional probabilities. And in the specific case of this 2 out of 3 system, this one will be always 0. So it is not possible that a component is inside a set of failure, and also it is right censored. In the case of this structure, this is not always true. It is just for this structure. And now our data is represented a little different. Now we have the times, the set of masked data, and the type of sensor, and if this component being in this set or not. So again, we have to change the way that we look to the problem to solve it. We also work with the complementary of this masked set. So we have, at the same time that we have the masked set who maybe produce the failure, we also have that one that we know that cannot produce the failure. And to solve this problem, here we can look. We need more samples because we have less information. And we need, our solution is using a latent variable. So we are building a variable called D because our solution here, it's almost the same that we did before. The difference is we will estimate this latent variable. What does this mean? Our likelihood, it's quite similar to what we have before. There is some changes, but what we are doing is, where we knew if it was sensor, if we're not sensor, or now we just need to add this, and when we have this latent variable, given this, we are in the same problem of before. So we will have as prior here, sorry, but these are all non-informative priors. It's just for an example. I again prefer informative priors, but okay. And we can work with Markov chains, Monte Carlo methods, but now not exactly the same multivariate metropolis hasting. Now we need the metropolitans with Gibbs, which is quite simple too, at least in my point of view. And our algorithm, in a simple way, is we generate the value of D. This value of D can be 0 or 1, failed or not. And this is just a Bernoulli random variable. We have all probabilities in conditional form. So for this latent variable, we have the full posterior. We know that, we know this distribution, so it is easy to use a Gibbs sampler here. And for the all parameters, when I give D, I can use the same idea as before. So we run this a lot of times, generating D, estimating the other parameters, generating D, generating parameters, and we go this interactively. Again, we were not necessarily a huge burn-in or jump of points, and we performed a sample size of time 1000. The same way we can use here to do the posterior expectation of reliability function. So we have, I will call your attention now. If you take attention of what I did now for MaxCAD system, I went faster here. I am not explaining with details. Why? Because it's exactly the same what we did before. The main important details, the main important detail here is this latent variable. Everything that we did until now can be used here. It's just this. Of course, it's just this. It's not just, but this is the solution. So again, how I can change my problem to bring a simple solution to it. And then we have the data, but now this is the interesting part. 16% was failed. 40% is left sensor. 6% it's right sensor. And from these all components, I also have 37% masked. This is where it started to quite be huge confusion here, because maybe masked, left, right, yeah, it is. And all of this is only 16% or 25% or 19% is observed, and there is a lot of missing information here. Sometimes the missing information is the type of sensor, sometimes I even don't know what I am missing. I just know a piece of all of this. And inside all of we did here, I could say, in my point of view, I am really impressed with the quality of these estimators. You can look at the component 1. Again, we are looking for marginal problems. We are looking for component, not for the system. In some way, well, is inside this credible set, credible region. Yeah, it's in the upper bound, but yes, it is. And if you look at the component 1 and component 2, this one is a little worse. Here is better in the end and worse in the beginning. And here it's out. Yes. And this one is worse in the beginning, worse but good in the middle. Okay, so what I could say now, it's a 300 sample size. And yes, of course, this may not be a huge good, but we are looking for the reliability functions. If you look at, for example, to expected mean time of the system, then you have a great estimator. So trying to find the distribution that generated the time failure of that component under this a lot of missing information, I can say that, yes, this is quite good. I don't have a measure of quality here yet, but yes, it is quite good. So I will have one friend of mine here saying that I don't have more time. So I will go fast in this example. This is through a real-world problem data set of failure times in hard drivers in computer system. They may have masked by the component 1 or 3 was the producing the failure, or all 3 components was producing the failure. So I don't know which one was producing the failure. The data is writing like this. We have also a lot of missing information, the same likelihood, and here is an important picture because, of course, we could do this huge size here in this axis, but what we are saying here is for the real problems, the only option that I have now is to believe in that because I cannot say this is good or not good. Also to do something like a good fitness analysis. How I can do good fitness analysis if I don't have the information of my sample? So, wow, the observed time was good fitted. I don't know what is the observed time. So this is also an important problem to try to look forward and see other possibilities to have a measure of quality here. Yes, we don't have it yet. So the main idea is this. The reference that we used for these 2 days was mainly that. And to build this work, well, you can see here that we are working in this kind of problem for some long time, maybe 15 years. So this is the main papers that we wrote and came to this until now. So thank you. And this is the main message of the tutorial. Try to find a way to look into the problem and how I can change it to a simple solution, or how can I bring to the simple solution. This is, at least for me, the most important part. Not exactly the reliability things, but how I can solve it. I can say one more thing that it is. We may not yet solve the reliability problem. We will still need more steps to have a great solution for this problem. But we are already getting a point that we have something useful. So, okay, we can go further, but it's already quite well in my point of view. Thank you.